Hello there, and welcome to the Galaxy Scientist. I'm glad you've slipped into this small pocket of quiet with me tonight. Outside, the solar system turns in its steady rhythm, 4 rocky worlds circling the same star. Like beads on an invisible thread, we grew up with their names in school. Mercury, Venus, Earth, Mars. Familiar, almost simple. But the truth of these Tellurian planets is stranger, harsher, and more beautiful than the neat diagrams ever showed. Tonight, we're going to wander into the corners of their story that rarely make it into textbooks, what they didn't teach you in school about the Tellurian planets. The hidden scars under the clouds of Venus, the burned and battered face of Mercury, the quiet restlessness under Earth's crust, the long-forgotten rivers on Mars. If this kind of soft, unhurried journey through the inner worlds brings you ease or curiosity, a gentle like and a quiet subscribe help others find their way here too. For now, we'll move slowly and begin. Everyone grows up knowing the name of the first planet. Mercury feels like an old figure from school, charts and simple diagrams. A small, bright point hugging the sun and carrying the name of a swift Roman god. People have watched it for thousands of years at dawn and dusk, slipping in and out of view near the glare. It is not hidden, not rare, and yet, among the rocky worlds, it is still the least explored. Only 2 spacecraft have ever visited it closely. It is tempting to imagine that this is because Mercury is plain, just a scorched little rock circling too close to the sun to be worth the trouble. But when you lean in, the picture becomes more layered. You can start with the simplest image, the innermost planet. Small, hard, airless. That sketch is not wrong, but it leaves out some of the most quietly interesting details. Under the harsh sunlight and deep shadow, this world has its own personality. In many pictures, Mercury does resemble our moon. It carries a round, cratered face, with dark plains and lighter highlands. At first glance, it looks gray and worn, but when you see it in true color, it is not just a flat slate. Gentle browns, muted tans, and slightly bluish patches show up across its surface. The colors are subtle, but they hint at different minerals and histories, painted not in bright strokes, but in soft, weathered tones. Beneath that skin of rock, Mercury's structure is unusual. It is not mostly stone with a small metal center, the way many people picture a rocky planet. By mass, roughly 70% of Mercury is metallic, mostly iron, and about 30% is silicate rock. It is, in a very real sense, more metal than rock. Because of this, Mercury is extremely dense, with an average density almost as high as Earth's. If you could somehow inflate Mercury to Earth's size, without changing what it is made of, you would feel almost the same pull at your feet. But Mercury is much smaller, so the gravity on its surface settles to about 3.7 meters per second squared. You would feel lighter than you do on Earth, though not as light as you might expect for such a small planet. Its surface gravity is only a little bit weaker than that of Mars, even though Mars is noticeably larger. That contrast quietly tells you how tightly packed Mercury must be, how much mass has been gathered into that small sphere. Its compact weight also means that even some larger moons, made of lighter ice and rock, end up having less mass than this small, metal-rich world. Turning your eyes back to Mercury's surface, you step into a landscape shaped early and left almost unchanged. The planet is covered with impact craters of every size, from tiny pits to enormous basins. There are wide, dark plains formed by ancient lava flows that once spilled out, cooled, and froze into smooth sheets of basalt. These features together tell you that Mercury has been geologically quiet for billions of years. With no thick atmosphere to erase scars and no active plate tectonics to recycle the crust, the record of ancient impacts remains written in stone. Even so, there are signs that Mercury was once far more active. One of the most distinctive of these is the presence of long, narrow cliffs and ridges, called scarps, that curve across the planet's surface. Some stretch for hundreds of kilometers, cutting straight across craters and plains. These scarps formed as Mercury's interior cooled and shrank slightly, causing the brittle outer shell to wrinkle and fold. In those slow, frozen folds, you can read the story of a world that has been contracting, the way dried fruit gathers creases as it loses moisture. Among all of Mercury's scars, one stands out: the Caloris Basin. It is an enormous impact basin, about 1,550 kilometers across, one of the largest known in the solar system. The event that created it released an incredible amount of energy. It did not just carve a hole, it shook the entire planet. The impact triggered lava eruptions that later filled parts of the basin's interior, and it raised a ring of mountainous terrain around the rim, in some places more than 2 kilometers high. On the exact opposite side of Mercury, at the point directly across from Caloris, the surface looks very different from the surrounding land. This region, often called weird terrain, is full of jumbled hills and broken ground, unlike the smoother plains elsewhere. Many scientists think that seismic waves from the Caloris impact traveled through Mercury's interior, converged at the antipode, and shattered the crust there. One violent moment on one side of the planet left a confused, crumpled signature on the other. If you imagine standing somewhere on Mercury's surface, the most immediate experience would be the temperature. With no substantial atmosphere to soften or spread the sun's heat, the difference between day and night is extreme. In places under the full midday sun, the temperature can climb to about 400 degrees Celsius. On the night side, without any blanket of air to hold the warmth, it can drop to around 163 degrees Celsius. The poles stay colder still. There, the temperature often remains near 93 degrees Celsius or below, because the sun never rises high in the sky. These sharp contrasts exist because Mercury cannot keep a thick atmosphere. The planet is small, its gravity relatively weak, and it sits very close to the sunday. Any gas that gathers around it is quickly stripped away by solar radiation and the constant flow of charged particles in the solar wind. There is nothing to trap the heat on the day side or to spread it around the globe, so the warmth simply radiates away into space once darkness falls. Even so, Mercury is not completely bare. Instead of a true atmosphere, it has an exosphere, an extremely thin envelope of atoms and molecules held loosely by gravity. In this exosphere, particles are so sparse that they almost never collide with each other. They do not form winds or clouds. They simply drift in near vacuum, tracing faint paths above the surface. Some come from rocks hit by micrometeorites. Some are knocked loose by the solar wind. Some are released directly from the soil by the heat of the sunday. Spacecraft like NASA's Messenger have captured images that hint at this ghostly shell. When the solar wind sweeps past Mercury, it can strip atoms from the exosphere and drag them away, forming a thin tail of material streaming behind the planet. In that sense, Mercury shares a feature with comets, a slender trail of atoms torn loose by sunlight and particles, stretching out into the dark. Earth has an exosphere as well, beginning hundreds of kilometers above our surface, where the atmosphere thins into space. For us, it is the boundary between air and vacuum. For Mercury, This boundary is almost all there is. The exosphere is not stable or permanent. Atoms are constantly being lost and constantly being replaced in a quiet, continuous exchange between the surface, the sun, and space. In the permanent shadows of some craters near Mercury's North Pole, there is another surprise. Because the planet's axis is almost upright, sunlight never reaches the deepest parts of these polar craters. They remain cold and dark, acting as natural traps for volatile materials. Radar observations and later measurements have shown that water ice lies hidden there, preserved in places where the temperature stays far below freezing. On a world that can scorch to hundreds of degrees in sunlight, pockets of frozen water survive in the most sheltered corners. Around the planet, shaping the way it interacts with the solar wind, is one more unseen layer, a magnetic field. Mercury has a global magnetosphere, a protective bubble formed by its magnetic field, pushing against the flow of charged particles from the Sun. This field is much weaker than Earth's, about 1.1% as strong, but still enough to divert some of the solar wind and create a complex, changing environment around the planet. The very existence of this field suggests that Mercury's large iron core is at least partly molten and moving, generating magnetism deep within. If you move your attention outward and watch Mercury travel around the Sun, its path is not a neat circle, but a stretched ellipse. Among all the planets, its orbit is the most eccentric. At its closest point to the Sun, Mercury is about 46 million kilometers away. At its farthest, about 70 million. The Sun, therefore, sometimes appears larger and brighter in Mercury's sky, sometimes a little smaller and dimmer, depending on where the planet is in its orbit. Mercury completes one lap around the Sun in about 88 Earth days. That is its year. But the way the planet spins while it orbits is one of its most unusual traits. Mercury is locked into a 3-to-2 spin-orbit resonance. It rotates 3 times on its axis for every 2 times it goes around the Sun. One full rotation relative to the distant stars, a sidereal day, takes about 59 Earth days. There is another timescale to think about as well, the synodic period, the time between one good alignment of Mercury and Earth and the next. That period is about 116 Earth days. Because of this, early astronomers who looked at Mercury during these occasional favorable viewings tended to see nearly the same face of the planet each time. Mercury is always close to the Sun in our sky, and the windows for observation are short. Seeing similar surface markings again and again led many to believe that Mercury kept one hemisphere facing the Sun all the time, the way our moon keeps one face turned toward Earth. It was only when radar observations were made, sending radio waves to bounce off Mercury and measuring their echoes, that the real rotation rate became clear. Those measurements showed that Mercury turns a little faster than it orbits. It is not tidally locked, but instead follows that 3-to-2 rhythm. Earlier ideas fell away as new data revealed the planet's true spin. If you could stand on Mercury and watch the sky long enough, the pattern of day and night would feel very strange. Because of the 3-to-2 resonance and the shape of the orbit, the time from one sunrise to the next, a solar day, is about 2 Mercurian years. The Sun would rise slowly, climb in the sky, and then, as the planet approached its closest point to the Sun, its apparent motion would slow, stop, and even reverse for a while. Around perihelion, Mercury's orbital motion briefly outpaces its rotation, making the Sun seem to move backward before it resumes its usual path towards sunset. Night would last just as long, stretching over another full year. Seen from above, you would notice that Mercury's orbital plane is tilted about 7 degrees relative to Earth's. Because of this inclination, the planet usually passes a bit above or below the straight line between Earth and the Sunday. Only when everything lines up just right do we see Mercury cross directly in front of the Sun's disk. From our point of view, a small dark dot gliding across the bright face. These transits are uncommon, happening on average about once every 7 years. Mercury's axis itself is tilted by only about 0.027 degrees, far less than Earth's or even Jupiter's. With so little tilt, the planet has almost no seasons as we know them. The pattern of sunlight over the course of its year barely changes, which is why those polar cold traps can remain in permanent shadow for so long. From Mercury's neighborhood, if you turned and looked back toward home, Earth would be nothing more than a bright star in the black. When the Messenger spacecraft was out near that inner orbit and glanced over its shoulder, it captured our planet as only a few pixels. In that tiny patch of light, aside from the babies not yet born, every one of us was there. Every ocean and cloud, every city and quiet room, every person listening to stories about distant worlds under their own familiar sky. That little image is a good way to remember what Messenger really was. It wasn't just a camera happening to catch Earth in passing. It was the quiet traveler that finally turned Mercury from a bright speck and a half-drawn map into a real, detailed world. Most of what we now know about the innermost planet, the close-up views of its craters and plains, the careful measurements of its gravity and magnetic field, the discovery of ice hiding in permanent shadow rests on the work of that one small, patient spacecraft. In the early years of planetary exploration, Mercury had to wait. Our first successful planetary visitor went to Venus in 1962, then to Mars in 1965, and Jupiter in 1973. Only in 1974 did Mariner 10 swing past Mercury. That order feels odd when you remember how close Mercury really is. Mercury can come closer to Earth than any other planet, while Jupiter is many times farther away and yet received repeated visitors. It wasn't because Mariner 10 had revealed everything. It only flew past Mercury and mapped about 40 to 45% of its surface. More than half the planet remained unseen. The real problem was that Mercury is one of the hardest worlds to orbit. It lives deep in the Sun's gravity well. A spacecraft falling inward toward Mercury is pulled faster and faster by the Sun's gravity. To slow down enough to be captured by Mercury's own small gravity, you would have to burn an enormous amount of fuel. Fuel is heavy, and for spacecraft, weight is an unforgiving limit. The heavier the craft, the larger and more expensive the rocket required to launch it. For decades, mission designers could not see a way to give a Mercury-bound probe enough fuel to slow down at the end of its journey, without sacrificing the instruments that would make the mission worthwhile. So after Mariner 10's brief visit in the mid-1970 seconds, Mercury exploration simply paused. In 1985, an orbital mechanics expert named Chen-Wan Yen found a gentler approach. Instead of fighting the Sun's gravity with huge bursts of thrust, she traced out a path that would use gravity itself as a series of brakes. In her plan, a spacecraft wouldn't race straight to Mercury at all. It would loop around the Sun many times, skimming past planets along the way and trading small bits of its speed with each encounter. Under this scheme, the craft would orbit the Sun about 15 times, flying past Earth once, Venus twice, and Mercury 3 times, before finally slowing down enough to be captured on the 4th Mercury encounter. Each flyby would bend the spacecraft's path and adjust its speed. The full route would span around 7.9 billion kilometers and take roughly 6.5 years. turning an impossible fuel problem into a manageable one. In 1998, NASA began to examine this route seriously. The path was complex, but did not require new technology, only careful planning and a spacecraft built to survive years of intense sunlight. Out of that work came Messenger, short for Mercury Surface, Space Environment, Geochemistry, and Ranging, launched in 2004. Messenger was a compact spacecraft, about 1.9 meters long and 1.3 meters wide, with a mass of around 1,100 kilograms. It carried a main engine, a heat shield of ceramic fabric to face the sun, 2 broad solar panels, and instruments to study Mercury's surface, exosphere, magnetic field, and interior. The goal was to learn what Mercury is made of, how it has changed, and how it behaves in the harsh space close to the Sunday. During its first year, Messenger made one full orbit of the Sun and then flew past Earth again. Gravity from Earth bent the spacecraft's trajectory, setting it on a new path inward, and the familiar view gave scientists a chance to test the instruments. Messenger took pictures of Earth and the Moon and measured our atmosphere and magnetosphere. As it moved closer to the Sun, Messenger used its solar panels for more than just electricity. Sunlight carries a tiny pressure when it strikes a surface. Over years, that push becomes noticeable. By angling its panels just right, the spacecraft could use this gentle force, like a small sail, helping to counter the sun's pull and saving propellant. In 2006, Messenger reached Venus for its first flyby there. At that time, Venus was on the opposite side of the Sun from Earth, so the spacecraft was out of radio contact during the closest approach. It still took images and gathered some data, but the encounter mainly let Venus's gravity reshape its path. A second flyby of Venus in 2007 came with better geometry. By then, the European Space Agency's Venus Express spacecraft was in orbit. For a short while, both missions observed the same world together, making coordinated measurements of the charged particles and magnetic fields around Venus before Messenger moved on. Then came the series of meetings with Mercury. On the 14th of January 2008, after looping through the inner solar system for years, Messenger flew past Mercury for the first time. It captured images of regions that had never been seen before and measured the planet's surface and surroundings in new detail, all while Mercury's gravity slowed and redirected it. A second flyby went smoothly as well, adding more coverage and refining the spacecraft's orbit around the Sunday. The third flyby, in 2009, brought an unwelcome surprise. During that pass, Messenger went into safe mode, a protective state where most activities are shut down to preserve the spacecraft if something seems wrong. For about 7 hours, the mission team could only wait and watch limited telemetry. The problem was tied to power management. During the flyby, Messenger entered Mercury's shadow, and for about 18 minutes, its solar panels could not see the Sunday. The spacecraft had to run entirely from its batteries, and a configuration issue in the software made the situation look unsafe. Out of caution, the onboard computer put itself into safe mode. Once Messenger emerged from the shadow and its panels started charging the batteries again, the computer reset and normal operations resumed. The spacecraft had come through its scare. It continued along the planned path, swung once more around the Sun, and prepared for the maneuver that would turn it from a visitor into a long-term companion of Mercury. On the 11th of March, 2011, after 6.5 years in flight, Messenger fired its main engine and slipped into orbit around Mercury. The orbit chosen was highly elliptical, carrying the spacecraft as close as about 200 kilometers above the surface at one end. and as far as about 15,000 kilometers at the other. This was a compromise between getting near enough for detailed measurements and staying far enough away to cool down. Mercury's sunlit surface and thin exosphere reflect and radiate a great deal of heat, and the sun there shines about 7 times brighter than from Earth's distance. By dipping in close for part of each 12-hour orbit and then retreating, Messenger could gather data without overheating. The prime mission was planned to last 1 Earth year. Instead, the spacecraft remained in orbit for 4. Orbit after orbit, it mapped Mercury's surface, probed its gravity, sampled its exosphere, and watched how the planet and its magnetic field responded to the changing solar wind. Before launch, 1,000 images would have been considered a success. By the time the mission ended, Messenger had sent back more than 200,000, giving us a nearly complete, high-resolution map of Mercury. As the years passed, the fuel that had been conserved so carefully began to run out. Each small burn to adjust the orbit or hold it up against Mercury's pull drew from the same limited supply. By late 2014, Messenger's closest passes brought it to just about 25 kilometers above the surface, skimming low over craters and cliffs. On the 25th of December 2014, the team commanded one last burst from the thrusters to raise the orbit slightly and extend the mission. Eventually, the tanks were empty. With no more fuel to counter the downward tug, the orbit slowly shrank until, on the 30th of April 2015, Messenger struck Mercury's far side and fell silent. There was no way to see the impact directly from Earth, but the timing and tracking made its fate clear. After a long journey, the spacecraft had finally joined the world it had been studying. Long before that final moment, though, Messenger had completed its main work. Among its instruments was a magnetometer, designed to measure Mercury's magnetic field in detail. From orbit, the spacecraft traced the shape and strength of the planet's magnetosphere, the bubble carved into the solar wind by its internal dynamo. The data confirmed that Mercury has a global magnetic field, generated by a partially molten iron core that is still slowly moving and conducting. On Earth, our relatively rapid rotation and the steady tidal pull of our moon help stir and heat the core, keeping the dynamo active. Mercury has neither a large moon nor a fast spin. Instead, its highly eccentric orbit appears to play an important role. As Mercury moves closer to and farther from the Sun along this stretched path, the Sun's gravitational pull on it changes slightly. Those changing tides flex the planet over long timescales, producing friction and heat in its interior. That repeated squeezing seems to help keep parts of the core liquid and the magnetic field alive. Messenger also found that Mercury's magnetic field is not centered. The magnetic dipole is shifted northward by roughly 20% of the planet's radius. The reasons for this offset are still not fully understood. The field itself is only about 1% as strong as Earth's, but even so, it is strong enough to deflect much of the solar wind around the planet. Because Mercury orbits so close to the Sun, the solar wind there is more intense than near Earth. Combine that stronger flow with a weaker magnetic field, and you get a magnetosphere that is pressed close to the surface on the day side and drawn out into a long, thin tail on the night side. Earth's magnetosphere extends many planetary radii into space. Mercury's hugs tight, compressed, and easily disturbed. This closeness makes Mercury's magnetic environment especially lively. Changes in the solar wind can reshape the magnetosphere quickly and often. One of the key processes Messenger observed is called magnetic reconnection. It happens when magnetic field lines from the Sun and from the planet are forced together, break, and connect again in a different pattern. When they do, stored magnetic energy is released, and some of the charged particles from the solar wind gain access to the region behind the planet, streaming along the magnetotail in thin, hot flows of plasma. Around Mercury, such reconnection events seem to be about 100 times more common than around Earth. Even here, on a small, sunlit world that once seemed like a simple rock, the space around it turns out to be full of motion, a quiet dance between gravity, heat, and invisible lines of magnetism that weave Mercury into the wider life of the solar system. Another thing Messenger discovered, while looping again and again through Mercury's tight magnetic cocoon, was that this cocoon isn't quiet. The spacecraft kept seeing brief flares of energetic electrons, each burst carrying hundreds of thousands of electron volts. Over the course of the mission, thousands of these events were recorded, mostly clustered in the northern hemisphere and squeezed close to the planet on the sunward side. No one has fully untangled the pattern yet, but the best idea is that they are born far behind Mercury, in its magnetotail, where magnetic field lines are stretched, snap, and reconnect. In those breaks, some electrons are suddenly flung along the planet's field lines, curling from the South Pole to the north like invisible beads sliding along a wire. Messenger also carried a suite of spectrometers, quiet, patient instruments that read the colors of light coming from Mercury's surface and exosphere. From those subtle shades, they could tease out which elements were present, even from orbit. And what they found was not the simple, baked rock many people expected. Mercury's crust is rich in volatile elements, materials that you might think should have been lost long ago in such heat: potassium, sodium, magnesium, sulfur, chlorine. They show up in unexpectedly high amounts, higher than on any other rocky planet in some cases, and far higher than on our moon. The ratios of these elements look, in some ways, more like Mars than like Earth or Venus. That alone was enough to overturn several comfortable theories about how the inner planets formed and how much delicate material Mercury ought to have kept. These volatiles are constantly being bombarded by intense sunlight, especially near the equator where the sun hits hardest. There, atoms like potassium are heated until many are shaken free from the surface, drifting up into the exosphere. Near the poles, where the sun's rays skim low and the surface stays cooler, more of that potassium can remain in the ground. This helps explain why Messenger saw some elements more abundant at higher latitudes, particularly in the north, than in the scorching equatorial zones. Temperature quietly sculpts the chemistry of the planet's skin. The exosphere, that fragile veil around Mercury, holds many of the same ingredients found in the rocks below sodium, potassium, magnesium, and others. But it is in constant flux. Charged particles from the solar wind grab ionized atoms and carry them off into space. Sunlight itself pushes gently on neutral atoms, giving them just enough of a nudge to drift away. If nothing replaced them, the exosphere would vanish in short order. It survives because the surface, micrometeor impacts, and the solar wind all keep feeding it, one atom at a time. Some of what Messenger saw there does not come from Mercury at all. Hydrogen and helium appear in the exosphere, even though they are not significant parts of the crust. Their source is the Sunday. The solar wind, made mainly of those two elements, washes over Mercury. A small fraction of those particles are slowed, captured briefly, and join the exosphere before slipping away again. In that way, the thin envelope around Mercury is part planetary breath, part borrowed starlight. By tuning its spectrometers to particular wavelengths, Messenger could watch specific elements in motion. Calcium showed a curious rhythm, more abundant in the exosphere at dawn than at dusk, hinting at processes, perhaps micrometeorite hits or fresh heating, that wake with the first light. Magnesium was seen streaming away from the night side, a delicate flow of atoms peeling off into space. Mercury's long, ghostly tail, made of escaping atoms, had already been glimpsed from Earth. Viewed through special filters, sodium glows softly as it trails behind the planet, making Mercury look almost like a comet. If you could stand on the night side with eyes sensitive to that light, the sky might hold a faint yellow wash, something like the distant suggestion of city lights on a hazy horizon. This tail changes over the course of Mercury's year. Because the planet's orbit is so stretched, both its distance from the Sun and its speed vary. The brightest sodium emission doesn't happen when Mercury's closest to the Sun, as you might expect, but when it is at an intermediate distance. In that middle stretch, the balance between sunlight, solar wind, and motion seems just right to lift sodium from the surface and fling it into space more efficiently. Even here, in an almost airless world, there are seasons of escape. Among all the exospheric ingredients, one was especially surprising: water vapor. On a planet where daytime temperatures can reach about 430 degrees Celsius, water sounds like something that should have boiled away long ago. And yet, hints of water vapor appeared in the data. Some of it may come from icy grains shed by comets that wander near Mercury's orbit. Some may be linked to the water ice, known to be trapped in the polar craters, tiny amounts liberated by micrometeorite impacts or other processes before drifting off. Decades before MESSENGER, the Arecibo radio telescope on Earth had seen bright radar reflections from regions near Mercury's poles. These patches behaved the way ice does when probed with radar. When MESSENGER began sending back detailed images, those reflective regions lined up neatly with craters whose floors never see direct sunlight. Inside those permanently shadowed basins, temperatures stay cold enough for water ice to endure, perhaps for millions or billions of years. Estimates suggest Mercury may hold roughly 1,000,000,000,000 kilograms of ice in such traps. On Earth, that would be a small reservoir. On Mercury, it's an astonishing storehouse, especially for any imagined future visitors in need of water. MESSENGER's cameras also showed something entirely new: bright, irregular, shallow depressions scattered across many parts of the planet. These features, called hollows, don't look like ordinary craters. Their edges are uneven, their interiors unusually bright, and they often form clusters on the central peaks or walls of older impact craters, where deeper material has been brought close to the surface. The leading idea is that hollows form when volatile rich rock is exposed to the fierce environment at Mercury's surface. Over time, those volatile components slowly escape, sublimating away under heat and radiation, and the rock left behind collapses, leaving pits where solid ground once was. Because hollows appear so sharp and fresh, they seem to be among the youngest features on the planet, possibly forming even now. In the middle of an ancient, cratered landscape, these bright patches whisper that Mercury is still, in its own quiet way, changing. Beyond the hollows, MESSENGER found extensive evidence of volcanism and slow global shrinkage. Large stretches of smooth plains, many with subtle color differences from their surroundings, are now understood as old lava flows. Frozen seas of rock that once welled up from the interior. Threading through these plains and older terrains are long, cliff-like scarps, wrinkles where the crust has buckled as the entire planet has gradually contracted. By measuring these scarps and modeling Mercury's interior, scientists concluded that the planet's diameter has shrunk by more than about 14 kilometers since its outer shell solidified. As Mercury's core and mantle cooled, they took up slightly less volume, and the rigid crust had no choice but to fold and crack like the skin of a drying apple. The scarps that lace its surface are the lasting marks of that slow, inward settling. All of this volatile, rich rocks, ice in permanent shadow, bright hollows, vast lava plains, a restless magnetosphere came into focus because Messenger was willing to spend years circling a small, sun-baked world that most people rarely think about. Outside specialist circles, the mission is still surprisingly little known. Maybe the next visitor, ESA and JAXA's Bepi Colombo, now on its own long journey toward Mercury, will bring this shy planet a bit more into the public's nighttime stories. To imagine what Bepi Colombo will see, it helps to picture Mercury not just as it is now, but as it was when it was even hotter and more active. Today, the planet still reaches 430 degrees Celsius at noon, yet has ice tucked away in polar darkness and bears scars of contraction from cooling. Long ago, its interior would have been hotter, and molten rock would have moved more easily through its shell. When rock is heated enough, the rigid lattice that holds its atoms in place breaks down, and it becomes magma, a thick, glowing liquid. Magma forms at temperatures of at least around 600 degrees Celsius, sometimes up to 1,300 degrees, depending on composition. It is far more viscous than water, 10,000 to 100,000 times thicker, closer in feel to a very slow syrup or ketchup. But if there is enough of it, it still flows. As the top layer cools and solidifies, it forms a crust that insulates the liquid beneath, letting it move along under its own weight, seeking low ground. On Mercury, one of the clearest records of such flows lies in craters like Raditladi. This basin is relatively young, likely less than 1 billion years old, with sharp walls and a floor that hasn't been heavily reworked by later impacts. Outside its rim, the terrain is rugged and jumbled. Inside, much of the floor is smooth, like a hardened lake. It's unlikely that the impact alone carved such a flat surface. The more likely story is that, after the asteroid struck and hollowed out the basin, molten rock flooded in. Lava, drawn downward by gravity, spread out and leveled itself, then cooled and froze into place. That smoothness is a quiet signature of a once moving sea of magma. Where did the lava come from? There are two main paths scientists consider. One is that the impact fractured the crust deeply, opening routes for magma already present below to rise and fill the new basin, an impact triggering volcanic eruption. The other is that the energy of the collision itself melted a large volume of already hot crustal rock, turning it into impact melt, that then pooled and set. The real story is probably some mix of both. Deep magma, rising to meet rock that had been flash melted by the crash. Once you learn to read that smoothness as the memory of lava, you start to see similar stories everywhere. Craters such as Rustaveli, Copeland, Polygnotus, and Rachmaninoff show floors that have clearly been resurfaced by flows. In some, central peaks stick up through the flat layer like islands in a shallow pond, telling you that molten rock rose high enough to cover most of the basin, but not all. Rachmaninoff, in particular, reveals a more complicated history. Inside the basin, a ring of fractures and ridges forms a rough circle. These patterns suggest that magma didn't just pour in once and freeze. Instead, it pushed up slowly from below, domed the ground, cracked the surface, and then cooled again as Mercury's long days and long nights baked and chilled the crust in turn. Here, The energy from space impacts, and the heat from within work together, each shaping the landscape in its own time. Lava did not confine itself to craters. In places like the valley called Angkor Vallis, you can trace the path of ancient flows that moved across open terrain. There, smooth channels run from higher ground down into neighboring basins, frozen rivers of rock that once slid and glowed, filling lowlands and pooling in depressions. Over time, flows like these built up vast plains, covering large regions with a subtly different, more orangish tint. Messenger's color images showed that this gentle orange cast is a strong clue for past volcanic activity. Regions washed in that hue tend to mark where lava once stood in wide seas. From these clues, a picture emerges of early Mercury as even less forgiving than it is now, its surface often reshaped by eruptions, its airless horizons bright with cooling rock. One area, northeast of Rachmaninoff, caught scientists' attention late in the mission. High-resolution images revealed a blanket of fine, delicate material spread over the terrain. The textures and patterns didn't match ordinary impact debris. Instead, they resembled volcanic ash, tiny fragments of rock blasted into the sky and then settling back to the ground. The most natural explanation is that there were once explosive volcanic vents there, hurling out hot particles that later fell like a strange, incandescent snowfall. NASA scientists jokingly likened it to snow, though this snow would have been born in fountains of molten stone and would have landed on rocks already warm enough to glow. Fiery, hot, angry snow dusting the surface of a small, quiet planet, turning slowly through the light of its star. So on early Mercury, it wasn't only rivers and lakes of lava you'd be living with. There would have been times when ash, hot and glassy, fell out of a darkened sky, settling over craters and plains like a cruel kind of snow. The planet's volcanism had many moods: slow floods that filled basins, buried hills, and smoothed valleys, and brief, violent eruptions that tore pieces out of the crust and threw them far away. One of the strongest hints of those catastrophic eruptions is a crater called Navoi. At first glance, it looks like many others, a round depression with raised edges. But when scientists looked more closely, its shape sent a different message. Most impact craters on a solid, relatively cool surface form a central peak. The physics behind it is surprisingly elegant. When a meteorite slams into the ground, it excavates a bowl-shaped cavity. The walls crumble and slide inward as loose material rushes down under gravity. Landslides on all sides meet in the middle, and their combined momentum has nowhere to go but upward, piling material into a central peak. You can picture the same idea in water. Drop a stone into a pond, and the water rushes in to fill the hole, then collides in the center and springs upward in a secondary splash. On solid ground, the splash doesn't fall back and vanish. The debris locks into place and becomes a permanent central mound. Depending on the angle and speed of the impact, that peak can be nearly circular or stretched into a teardrop shape. But some sort of uplifted center is the usual outcome. Navoi doesn't follow that rule. Its inner structure and central formation are irregular, missing the clear, symmetric peak you would expect if a rock from space had done the carving. When Messenger's images were studied in detail, the best explanation that emerged was volcanic, not impact-related. Navoi appears to be a caldera, a crater not punched in from above, but blown out from below by an eruption so intense that it emptied and collapsed a chamber of magma. With a diameter of about 66 kilometers, the eruption needed to create such a void and scatter its debris for many kilometers around must have been truly enormous. Add that to the other clues: lava-flooded basins, ash-covered plains, subtle orange volcanic seas, and a picture forms. Early Mercury knew meteors raining from space, striking with enough energy to melt rock. It knew slow, bubbling magma filling lowlands, rivers of lava flowing like glowing syrup toward distant basins. It knew explosive vents that choked its thin skies with hot particles, and craters whose very walls might one day fracture, collapse, and give way beneath your imagined feet. For a time, this really was a melting planet. Now, the stage is quieter. As far as we can tell, Mercury no longer has active volcanoes. Its interior has cooled enough that the violent outbursts have faded. The sun still bakes its dayside, but the deep, raw fury that once stirred inside seems to have calmed. What remains is a kind of stillness, and in that stillness, traces, the scars on its surface, calderas, hollows, wrinkle ridges, and lava plains are the pages of a long geological diary written when the planet was much more restless. Because Mercury is so difficult to reach, each piece of that diary has been hard-won in all of human history. Only 2 spacecraft have ever visited it. Mariner, 10 inches, the mid-1970 seconds, and Messenger, which orbited Mercury from 2011 to 2015. A third mission, Bepi-Colombo, is now on its way and scheduled to arrive in the middle of the decade. Of the first 2, only Messenger actually settled into orbit, circling the planet over and over. That makes it the only mission so far to give us detailed, global, close-up views of Mercury's surface. Even with those years of data, some of the formations Messenger revealed are still unsolved puzzles more than a decade later. Others are clearer, showing in simple ways just how fierce and formative the early solar system must have been. If you step back and look at Mercury's face with that in mind, a few things stand out almost immediately. Color, for one. Mercury isn't really a flat gray ball. In enhanced images, its surface is mottled with speckled grays, creams, and beiges, with lighter streaks and darker patches. The dark areas are thought to be rich in carbon, particularly graphite, the same form of carbon that ends up in pencils. Long ago, a graphite-rich layer may have floated to the top of Mercury's early magma ocean and become part of its crust. Later impacts then broke and mixed that layer, painting the surface with darker, carbon-heavy material. The lighter areas, which we'll come back to later, tell their own story. But even before you think about composition, you can't help but notice the craters. Like the Moon, Mercury is blanketed in them. Circular wounds where ancient pieces of rock, metal, and ice slammed into the planet at tremendous speeds. Over time, as the impacts accumulated, they made a kind of record of everything that has crossed Mercury's path. Those craters aren't all the same age. You can get a rough sense of time just by looking at their rims. Young craters tend to have crisp, sharp edges, steep inner walls, and clearly defined structures. Older ones look softened, their rims rounded and broken, their shapes less distinct. Even without wind and rain, the surface of Mercury changes slowly. Micro-impacts, thermal stress from huge day-night temperature swings, and slow geological shifts all work over millions of years to blur the sharpness of once fresh features. Sometimes a new crater overlaps an older one. In those places, you can see 2 circles cutting into each other, their rims intersecting in a way that lets you tell which came first. the younger crater will slice across the older, hiding part of its rim. Scenes like this, layered impacts of different ages, hint that Mercury's surface has been active in a broader sense, not just through volcanism and contraction, but through the steady rain of debris from space. Despite having almost no atmosphere, Mercury's surface is not truly static. As the planet cools, its interior contracts, and the crust responds by wrinkling and bunching up. Those wrinkles appear as long scarps, cliffs that can stretch for hundreds of kilometers. They are one sign of motion. Another is slumping, where part of a crater wall slips downward under its own weight. Messenger captured a crater where this is beautifully clear. About a quarter of the rim remains intact, with its original shape preserved. The remaining 3/4 have slumped inward, sliding down toward the basin floor in a broad, broken arc. What remains is a lopsided structure, one segment still high, the rest collapsed. No one is entirely sure why only part of the rim gave way. Maybe the rock is different there, more stable in composition or structure. Maybe the direction and energy of the impact set up particular patterns of stress. For now, it remains a quiet question, hanging over a frozen landslide. That sense of unfinished understanding is part of Mercury's charm. Again and again, you find features that invite you to guess, to compare, to imagine how they formed, without giving you the full explanation. One such set of features is familiar from the Moon as well: crater rays. Crater rays are bright, spidery lines that radiate outward from certain impact sites. From orbit, they look like fine, pale threads spreading over the darker ground, sometimes stretching hundreds of kilometers. Their light color suggests that they are composed of material dug up from below the surface rock that hasn't been as darkened by long exposure to space weathering or enriched in graphite like the uppermost layer. On Mercury, many ray systems stand out sharply, making them one of the planet's most distinctive visual traits. For a long time, though, scientists had trouble recreating them. In laboratory experiments, researchers tried different impact speeds, different projectile sizes, and different kinds of target material. They would smooth out a bed of sand or powder, send a meteor into it, and film the results. The impacts made craters. They threw ejecta outward, but the debris fell in more or less continuous patterns, a ring or fan around the crater. The long, thin, filamentary lines seen on Mercury and the Moon just wouldn't appear. Then, in 2018, a researcher named Tapan Sabawala came across something intriguing online. A group of students had been doing simple impact experiments and had, almost casually, reproduced ray-like patterns that looked very much like the real thing. This was puzzling at first. How had they managed what dedicated lab setups had failed to capture? The difference turned out to be something small but important. In the more formal experiments, scientists had always carefully smoothed the sand before each shot, creating a clean, even surface. It made for neat, repeatable conditions, but it also erased one crucial ingredient: roughness. The students, by contrast, had left their sandbed in a more natural state, lumpy, uneven, full of tiny ridges and troughs. When Sabawala and others repeated the tests with deliberately rough surfaces, the thin, branching rays finally appeared. The lesson was simple and elegant. The formation of crater rays depends far more on the shape and roughness of the ground than on the exact speed, angle, or even composition of the impactor. When ejecta lands on an irregular surface, small differences in height and slope guide it into narrow channels, concentrating it into lines instead of smooth blankets. Once you know this, the ray systems on Mercury become even more impressive. Some, as you might remember, stretch more than 400 kilometers across the surface, and those are only the modest ones. The ray system from the crater Hokusai is vast, with bright streaks that run almost all the way around the planet. Remember that Mercury's circumference is about 15,000 kilometers. To paint rays on that scale, the impact that formed Hokusai must have been extraordinary. Another crater, Debussy, has its own extensive ray system, spreading more than 1,000 kilometers. While the Moon also has craters with rays, Mercury's are often larger and more dramatic. Together, they underline how important high-energy bombardment has been in shaping the planet's surface. Sitting so close to the Sun, Mercury is a natural target for objects spiraling inward. The Sun's gravity dominates, pulling comets and asteroids on steep, fast paths. Mercury's own gravity is relatively weak. It struggles to capture such objects as permanent moons. Most simply pass by, pulled onward. But if their path happens to cross the planet itself, the Sun's pull adds speed to the impact, making collisions especially powerful. This combination explains why visiting Mercury with a spacecraft is so challenging. You have to fight the same gravity that makes these impacts so fierce. But it also means that when Mercury does catch an incoming object, it often does so in the most direct way possible, by being in its way. Even with this understanding, not every feature can be explained as a simple impact scar. One of the most intriguing examples lies in a region around a crater called Apollodorus and a surrounding network of radial troughs known as Pantheon fossae. At first glance, Apollodorus might look like a fairly ordinary crater with some unusual cracks reaching outward. But the details are odd. The fractures that spread out around it and the many radial lines in the nearby terrain form a pattern that looks surprisingly like broken glass fine, radiating splits that fan away from a central point. Glass fractures like this because it is hard but brittle, able to hold a smooth surface until a stress suddenly makes it shatter. Elsewhere on Mercury, craters behave in a simpler, more familiar way. Most of them do not crack the crust into glassy shards. Instead, they spray out rays of ejecta or settle into neat, rounded bowls. That fits a world made mostly of loose, fractured material, a surface that behaves more like sand than like brittle glass. Sand doesn't shatter when struck. It splashes, it scatters, it slumps. That's why the fractured pattern around Apollodorus and Pantheon fossae is so unsettling. We don't see anything quite like it anywhere else on the planet. Mercury's crust, by and large, doesn't fracture that way under impacts. It gives, it flows, it crumples, but it doesn't normally split into those long, brittle-looking lines. You might wonder whether the surface there was unusually cold and rigid at the moment of formation. Nights on Mercury can reach around 180 degrees Celsius, and cold rock can be more brittle. But if temperature alone were the cause, we would expect to see similar fracture systems in other places as well. Roughly half of all incoming impactors strike the night side, yet this kind of pattern seems unique. The explanation, if it is tied to cold, must have something more particular to this region. When you look closely at Apollodorus, the crater sitting near the center of the radiating troughs, there is another twist. It doesn't sit exactly at the geometric center of the pattern. It's very close, but not quite right. If Apollodorus had created the whole network in a single event, you would expect a better alignment. That slight offset suggests that the crater and the spider-like fractures may not share the same origin. Something else might have formed Pantheon fossae first, with Apollodorus arriving later as a separate impact, near the heart of an already fractured landscape. If that's true, you're left with a subtle, nagging question. What could carve that shattered glass pattern without leaving its own obvious crater. One possibility is that the force came from below instead of above. Perhaps, long ago, magma rose in a broad, domed uplift, pressing gently but insistently against the overlying crust. As the crust stretched, it may have cracked outward in all directions, producing radial fractures like those in Pantheon fossae. Later, an asteroid struck near the center, leaving Apollodorus as a kind of punctuation mark at the end of a much older sentence. For now, that's just an idea, one of several. The truth is that Pantheon fossae remains a mystery. It is one of those places where the surface seems to say, something unusual happened here, without yet telling us what. Mercury still keeps secrets in its stone. New missions may help. When ESA and JAXA's Bepi-Colombo spacecraft arrives at Mercury, it will carry a fresh set of instruments and a different way of looking. It will study the planet's magnetic field and exosphere in even more detail, map its surface with new eyes, and probe its interior structure. Perhaps it will refine our understanding of how hollows form, how the crust has shrunk, and what exactly happened around Apollodorus and Pantheon fossae. Until then, scientists continue to sift patiently through the data that Messenger left behind. Gravity maps, magnetic readings, images in many wavelengths, each one a quiet clue. Mercury, meanwhile, goes on circling close to the Sun, enduring as it has for billions of years. It faces a furnace of light and charged particles every day, and a deep, airless cold every night. It absorbs impacts, shrinks slowly as it cools, and holds onto its thin exosphere against a constant outward pull. For a world so small and so battered, there is a stubborn resilience in that. The conditions that make Mercury hard to visit, its proximity to the Sun, its deep position in the star's gravity well, its stark temperature swings, are the same conditions it has lived with from the beginning. Its surface, charred and cratered, isn't just a scar record. It's a testament to how long a rocky planet can last in a harsh orbit and still quietly keep its shape. We sometimes talk about the first planet as if it were the simplest, as if everything interesting must lie farther out, where things are cooler and gentler. But Mercury shows that being closest to the fire can carve a world into something unexpectedly subtle, a place of molten pasts, fragile tales, bright hollows, and unexplained fractures that still invite late-night questions. And then, just a little farther from the Sun, there is another world that also wears a mask. From here on Earth, Venus looks soft. In the evening or before dawn, it hangs low in the sky as a brilliant point, dressed in a steady glow that feels calm and almost tender. Wrapped in thick clouds, it presents a smooth, unmarked face, and its name, borrowed from the Roman goddess of love, feels fitting at first glance. But if you could drift beneath that cloud layer, you would find something very different. Below the pale blanket, the air grows heavy and hot. Temperatures near the surface reach around 462 degrees Celsius, hotter even than Mercury's midday. The pressure is about 92 times that of Earth's sea level, roughly what you would feel a kilometer under our oceans. Volcanic features dot the landscape, and the atmosphere itself is laced with carbon dioxide and sulfur compounds. Venus is beautiful from afar, but up close it is one of the most hostile places in the solar system. Still, it is our neighbor. Venus orbits the Sun at an average distance of about 0.72 astronomical units, roughly 108 million kilometers or so. Its orbit is nearly circular, the least eccentric of all the planets, so its distance from the Sun hardly changes over the course of its year. At its closest to Earth, Venus comes within about 41 million kilometers, making it, at those times, the closest planet to us. You might imagine that Venus would be brightest in our sky precisely at that closest approach, but the geometry is a bit trickier. When Venus is nearest, it is almost directly between us and the Sun, so we mostly see its night side. Even then, some light filters around through its thick atmosphere, and the planet remains visible. But Venus actually shines most strongly when it appears in our sky as a thinner crescent, a little to one side of the Sun from our perspective. Then, it is close enough and illuminated enough that it outshines every other nighttime object except the Moon. That brightness has fooled more than a few people. Throughout the decades, Venus has often been reported as an unidentified light, hanging low over the horizon or seeming to follow someone driving along a dark road. Even experienced observers have been surprised by it. At the eyepiece of a small telescope, though, the illusion fades into something simpler and more intimate. The planet shows a clear crescent shape, like a tiny, distant moon made of daylight. Because Venus orbits inside Earth's path, there are rare times when it passes directly between us and the Sun and crosses the Sun's face. These events, called transits, are quiet spectacles. From Earth, Venus appears as a small, perfectly round black dot, moving slowly across the bright solar disk. Transits of Venus come in pairs, with each pair separated by more than a century. Within a pair, the two events are 8 years apart. The last ones were in 2004 and 2012. The next will not arrive for more than a lifetime. The rarity is caused by the slight tilt between Venus's orbital plane and Earth's, and by the rhythm with which Venus catches up to us roughly every 584 days. Most of the time, Venus passes a little above or below the Sun in our sky. Only when timing and alignment are just right does it cross directly in front. Like all the planets, Venus orbits the Sun in the same overall direction, anti-clockwise, viewed from above the Sun's north pole. But unlike most of them, it spins on its axis the other way. Its rotation is retrograde. If you could hover above Venus's north pole and watch, you would see it turning slowly clockwise. It also spins extraordinarily slowly. One full rotation with respect to the stars, a sidereal day, takes about 243 Earth days, longer than Venus's own year, which lasts about 224 Earth days. Because of that unusual combination, the length of a solar day on Venus, the time from one sunrise to the next, is shorter than the sidereal day, but still very long by our standards, about 117 Earth days. In the course of a single Venusian year, you would experience not quite 2 sunrises. The rotation is so gentle that at the equator, the surface creeps along at only about 6.5 kilometers per hour, walking speed for a human. This slow spin helps make Venus one of the most spherical objects in the solar system, smoothed by its own gravity. Why Venus rotates backwards is still not completely clear. Some models call on a giant impact billions of years ago that knocked the planet off its original spin and left it slowly turning in the opposite sense. Others point to complex tidal interactions between Venus, the Sun, and the planet's dense atmosphere, which could have gradually reversed and slowed the rotation over time. Whatever the cause, the result is a world that looks like a twin to Earth in size, but behaves very differently. Venus is only slightly smaller than our planet, with a diameter of about 12,100 kilometers compared to Earth's roughly 12,740. Its average density, around 5.3 grams per cubic centimeter, is close to Earth's 5.5, and the surface gravity is only about 10% weaker than what you feel here, roughly 8.9 meters per second squared. If you could somehow stand safely on Venus, your weight would feel very familiar. The air pressing down on you, though, would not. The atmosphere is nearly 93 times denser than Earth's, squeezed into a slightly smaller volume. Most of it is carbon dioxide, with clouds of sulfur dioxide and droplets of sulfuric acid floating high above the surface. All that gas traps heat with ruthless efficiency. Sunlight passes through the upper layers easily enough, but the infrared radiation that the surface tries to emit in return is absorbed and re-emitted over and over by the thick blanket of CO2. The result is the strongest greenhouse effect in the solar system. On average, the surface sits around 462 degrees Celsius, hotter than Mercury's dayside, even though Venus receives only about a quarter of the solar energy that Mercury does. The difference is Mercury's lack of an atmosphere. Its heat escapes freely into space once the sun sets. Venus, by contrast, hoards the warmth. Night and day, equator and pole, the temperature hardly changes. The planet is like a sealed oven that has been left on for a very long time. Venus's axis is only tilted by about 3 degrees, much less than Earth's 23.5 degrees, so seasonal shifts are minimal. The winds near the surface move slowly, just a few kilometers per hour, but the dense air means even a gentle breeze can push small rocks and dust, sculpting the ground over time. Higher up, in the cloud tops, the story changes. There, winds race around the planet at speeds up to about 300 kilometers per hour, circling Venus in just 4 or 5 Earth days. From orbit, you can see these high clouds streaming around the globe, making it look as if the whole planet is spinning quickly even while the solid body below turns at a crawl. Those clouds are made mainly of sulfur dioxide and sulfuric acid droplets. The rain that forms within them is not like rain here. Sulfuric acid is intensely corrosive, and although most of the droplets evaporate before they reach the surface, the thought of such a sky adds one more layer to the planet's harshness. From far away, Venus shines like a steady lantern in the evening. Up close, it is a world of crushing pressure, slow days, fast winds, and clouds of acid, holding its secrets behind a veil that reflects almost all the sunlight that dares to touch it. The clouds of Venus really are a kind of armor. They are so bright and thick that only about 10% of the sunlight that reaches them makes it down to the surface. The rest is scattered back into space, which is part of why Venus shines so fiercely in our sky. From orbit, those clouds form an unbroken blanket, hiding every mountain and plain from ordinary view. Lightning flickers within them, too less frequent than on Earth, but still there, silent from afar, threading through the sulfuric acid and carbon dioxide. High above the surface, near the South Pole, those winds and clouds fold into something even stranger, a great atmospheric vortex. In thermal images, it appears as a whirling structure, a storm in permanent residence over the pole. Saturn has its own polar patterns, many storms gathered into complex shapes, but Venus's vortex is more solitary, one vast twisting feature sitting at an altitude of roughly 59 kilometers just above the tops of the main cloud deck. That height is interesting for another reason. Around 50 to 60 kilometers above Venus's surface, the air pressure and temperature become surprisingly familiar. There, the pressure is close to what you feel at sea level on Earth. The temperatures range from warm to hot, but survivable by ordinary standards, and the gravity is only slightly weaker than ours. If it weren't for the chemistry of the air, mostly carbon dioxide, laced with sulfuric acid droplets, it would feel oddly comfortable. In daydreams, some scientists imagine floating stations or airships at that level, sealed and airtight, gliding in a layer where the outside environment is hostile in composition, but gentle in pressure and warmth. To understand what lies above and below that corridor, we've had to send machines into the clouds. Long before orbiters with radar and infrared eyes, there were the tough little landers of the Soviet Venera program. In the 1,960 seconds and 70 seconds, while the world's attention was often fixed on the moon, a series of spacecraft were quietly aimed at Venus. Many failed on the way or succumbed before touchdown, their signals fading into the noise. Then, in 1970, Venera 7 became the first probe ever to land on another planet and send back data from its surface. It probably toppled over as it hit, but before it died, it managed to report a temperature of about 475 degrees Celsius, confirming that the surface was hotter even than many had guessed, and that Venus's greenhouse blanket was as intense as theory suggested. Venera 8 followed and found that beneath the clouds, visibility was surprisingly clear. The main cloud deck ends high in the atmosphere, so at ground level the air, though thick and hot, is not opaque. Visibility of about a kilometer meant that future landers could carry cameras and reasonably expect to see the ground around them, rather than just a yellowish fog. Venera 9 sent back the first black and white images from the surface: blocky rocks, a flat horizon, a landscape that looked oddly like a volcanic desert on Earth, only under a dim orange sky. Later, Venera 10, 13, and 14 returned more pictures, including the first color views, along with detailed measurements of the atmosphere and soil. For a few precious minutes in each landing, the probes endured crushing pressure and blistering heat long enough to transmit a handful of scenes and numbers from a world that would destroy an unprotected human in seconds. Orbiters came later, armed with radar systems that could pierce the permanent cloud veil. By sending radio waves down and measuring their echoes, they built up maps of Venus's topography with remarkable clarity. Slowly, the outlines of continents, plains, and mountains emerged. The surface turned out to be dotted with large volcanoes, 167 of them more than 100 kilometers across. On Earth, the only volcanic complex comparable in size is the Big Island of Hawaii. This doesn't mean Venus is erupting more often than Earth today. Instead, it speaks to how its crust has behaved over long spans of time. Our planet has plate tectonics, big slabs of crust that move, collide, dive into the mantle, and rise again. That motion continually renews the surface on timescales of tens to hundreds of millions of years, erasing older structures and recycling rock. Venus seems to lack such plate tectonics. Its outer shell is thought to be more like a single stagnant lid. Heat builds up underneath, and instead of being released in many small ways along plate boundaries, it may be released in fewer, larger events. The age of Venus's crust, judged from crater counts and other clues, is estimated at roughly 300 to 600 million years. At some point in that window, something dramatic may have happened. The mantle beneath the crust heating until it forced its way up through widespread fractures, flooding most of the surface with lava. Today, about 80% of Venus's face is covered in volcanic plains-cooled lava that once flowed over vast areas. Scattered among them are hundreds of thousands of smaller volcanic features, domes, cones, and mysterious pancake-like structures. There are impact craters too, around 900 of them, but none smaller than about 3 kilometers in diameter. Any incoming object much smaller than about 50 meters across tends to break apart and burn up in the thick atmosphere before reaching the ground. Only the larger, sturdier impactors can punch through and leave scars. For a long time, scientists expected Venus to have a magnetic field similar to Earth's. The two planets are close in size and density, and both likely have iron-rich cores. Yet measurements showed that Venus has no significant global magnetic field of its own. Something in its interior history is different. We don't yet know exactly why. One idea is that the way Venus cools and rotates doesn't support the same kind of vigorous core motions that power Earth's dynamo. Another suggestion, based on some modeling work, is that our own magnetic field may have been helped along by the giant impact that formed the Moon, an event Venus does not seem to have experienced. In the absence of such a jolt, Venus's core might have evolved along a quieter, less magnetic path. Whatever the true cause, the effect is clear. With no strong internal field, Venus is directly exposed to the solar wind. The charged particles streaming from the Sun collide with its upper atmosphere and ionize parts of it, creating an induced magnetosphere, a magnetic bubble not generated from within, but shaped by currents in the ionized gas itself. Solar wind also strips lighter molecules from the high atmosphere and drags them away, forming a faint, elongated tail on the planet's night side, rather like a comet's. Under certain alignments, that tail can stretch far enough that its edge brushes past Earth's orbit, but it is too tenuous and energetic to be seen with naked eyes. To feel how all of this fits together, it helps to imagine falling through those layers with a small probe, the way Venera once did. Far above the clouds, at altitudes of around 250 kilometers, the atmosphere is barely there, a thin haze shading into space. 99% of Venus's atmospheric mass lies below this height. Up here, the probe meets wisps of gas, touches the first molecules of carbon dioxide, and begins to taste the difference from Earth. Temperatures swing widely between day and night, from around 37 degrees Celsius to 43 degrees Celsius, similar to what a high-altitude balloon might see in Earth's stratosphere, but carried in a very different chemical mix. In this high region, some oxygen atoms shine faintly in infrared light. Telescopes and orbiters see them as an airglow, a soft emission from excited atoms high in the sky. Images from missions like Venus Express show this glow as patches and bands of blue in infrared views, tracing out where reactions in the upper atmosphere are quietly releasing energy. As the probe descends, it enters the main cloud deck, beginning around 60 kilometers above the surface and extending down to about 40 kilometers. This is the source of the familiar mustard yellow veil that most pictures of Venus show. A thick layer of clouds made primarily of sulfuric acid droplets. Ultraviolet light from the sun breaks carbon dioxide into carbon monoxide and single oxygen atoms in these heights. Those atoms react with sulfur dioxide and trace amounts of water vapor to form the acidic droplets that fill the clouds. From outside, this deck looks almost uniform and impenetrable. About 3/4 of the sunlight that hits it is reflected away. Yet, when you look in different wavelengths, hidden structure appears. Infrared images, like those from the Japanese Akatsuki spacecraft, show bright and dark bands and whirling shapes, wrapping the planet in sweeping arcs. The bright regions mark warmer, deeper layers glowing through. The dark ones mark thicker or colder clouds that block the radiation. Deeper still, below the cloud base, the air clears again, but now the heat truly asserts itself. Carbon dioxide dominates here, and its density becomes so great that the distinction between gas and liquid begins to blur. Near the surface, at pressures around 90 times those at Earth's sea level and temperatures upward of 460 degrees Celsius, the CO2 behaves like a supercritical fluid, neither quite a gas nor a liquid, but something in between, with the ability to diffuse like a gas and dissolve materials like a liquid. The winds in this lower region slow down compared to the roaring superrotation high above. At the surface, they creep along at just a few kilometers per hour, but in such dense air, even a gentle breeze carries enormous force. Moving through it would feel like wading through water, surrounded not by cool liquid but by a clear, invisible medium hot enough to melt lead. Infrared observations from spacecraft passing by Venus show the lower atmosphere glowing intensely in certain wavelengths, especially around 2.3 micrometers. In those images, the deep layers appear as a reddish radiance, with darker patches marking where the higher sulfuric acid clouds block the view. The effect is like seeing a coal furnace through a lace curtain, a bright, uniform heat with patterns of shadow drifting above it. Within that furnace, the atmosphere is layered, each band with its own temperature, density, and chemistry, each reacting to sunlight and planetary heat in slightly different ways. In ultraviolet light, different aspects of those layers come out again: high-altitude hazes, mysterious dark streaks whose composition we don't yet fully understand, subtle waves and spirals that betray motions in the air. All of it, reflective clouds, polar vortices, lightning, supercritical gases, slow winds and fast, belongs to the same hidden world beneath that bright evening star you sometimes see from your window. From a distance, Venus is just a point of light following the sun across the sky. Up close, it is a deep, complex atmosphere wrapped around a volcanic surface, a place where physics writes its stories in heat and pressure instead of in gentle breezes and oceans, and where our quiet, robotic visitors have only just begun to read the first lines. When you look at Venus in ultraviolet light instead of ordinary, visible light, the clouds begin to show more personality. Images from spacecraft like Japan's Akatsuki, taken at wavelengths around 283 and 365 nanometers, don't glow with the dramatic contrast of the infrared views, but they're still more varied than anything you see in simple white light. Patches of darkness and smudged, blotchy regions appear across the cloud tops, places where ultraviolet light is being absorbed rather than bounced harmlessly back into space. What is doing the absorbing exactly is still not clear. The usual suspects, sulfur compounds, aerosols, tiny droplets, can explain part of the pattern, but not all of it. Some combinations of chemicals fit some datasets and fail others. There are hints that something in Venus's atmosphere, perhaps a mix of substances or particles we haven't fully pinned down yet, is quietly swallowing ultraviolet light. Even here, in a place we've been studying for decades, there are still ingredients that slip through our fingers when we try to name them. The atmosphere's strangeness deepens at the poles. In infrared images of Venus's north and south poles, each cap is marked by a great swirling structure, a polar vortex, about the size of a continent back home. These storms are not simple circles. They twist and fold, reshaping themselves over hours and days. Most unsettling of all, they often show not one central eye, but two, like a double pupil in a moving hurricane. Those twin eyes drift, merge, separate, and tilt. The whole pattern can change significantly in less than an Earth day, making it very difficult to model. Winds of about 100 meters per second whip around these vortices, feeding them, carrying heat and momentum from other parts of the atmosphere. We know they exist, we can watch them evolve, but the fine details, the exact balance of forces that keeps them double-eyed and restless, are still part of Venus's private language. Beneath that restless sky lies the surface, which we've only ever seen directly through the eyes of a few very brave machines. The thick sulfuric acid clouds prevent any ordinary camera in orbit from glimpsing the ground in visible light. So the only true surface photographs we have are from landers that actually touch down. Altogether, just a handful of images, 6 or so taken by 4 Soviet Venera probes, hold that honor. In those photographs, the air is unexpectedly clear. Scientists once worried that a dense haze or fog might limit visibility to a few meters, but that isn't what the landers found. The horizon is visible. Rocks, slabs, and soil can be seen stretching out tens or even hundreds of meters. Everything is tinted a dull yellow-brown by the thick, chemically rich atmosphere, as though the world were lit by a permanent, low sun filtered through smoke. The ground itself looks stark and dry. Broken stones sit on gently sloping plains that bear the texture of ancient lava flows, long since cooled, and then softly reshaped by the intense heat and pressure. There are no rivers, no trees, no sign of liquid water, only baked rock under a sky that presses down with almost 100 times Earth's sea level pressure. It's easy, standing there in imagination, to wonder if a world like this might echo our own future, billions of years ahead, when the sun grows brighter and any delicate balance we enjoy begins to shift. But the Venera landers could not stay long. Their metal shells were designed to survive not just hard landings, but also temperatures hot enough to melt lead and pressures that would crush an ordinary submarine. Even so, none of them lasted more than a couple of hours on the surface. Their electronics slowly overheated, their structures strained, and then their signals faded. The images and measurements they sent back in that brief window were precious, short, breathless glimpses into a place no human has ever stood. To see beyond those narrow snapshots, we turn to a different kind of vision. Neither ultraviolet nor infrared can cut cleanly through the clouds to map Venus's hills and plains. For that, we needed radar. Radio waves can pass through the sulfuric acid clouds and echo off the ground, carrying information about the shape and roughness of what they touch. The Soviet Venera 15 and 16 orbiters in the early 1980 seconds were among the first to use this technique systematically, producing maps with resolutions on the order of 1 to 2 kilometers. Later, NASA's Magellan spacecraft, circling Venus between 1990 and 1994, dramatically sharpened the picture. By carefully stitching together its radar swaths, Magellan mapped about 98% of the surface at a resolution down to roughly 120 meters. From that data, and from earlier missions like Pioneer Venus, scientists built composite images of an entire world. Volcanoes, coronae, fracture zones, impact craters, rift valleys, and vast, smooth plains all emerged from the fog, rendered as textures of brightness and darkness in radar. The result is a planet that looks young in geological terms, not because it is newly formed, but because recent volcanic resurfacing has erased many older scars. Radar showed us that Venus is not just a static rock beneath its clouds, but a place sculpted by colossal lava floods and broad uplift, where immense structures have been frozen in place by time. It's a different kind of beauty, hidden, harsh, but undeniably intricate. Even so, the questions that remain are large. In recent years, one of the most tantalizing has revolved around a single molecule, phosphine. In 2020, analysis of data from the James Clerk Maxwell telescope suggested faint hints of phosphine gas in Venus's upper atmosphere. On Earth, phosphine can be produced by certain industrial processes and by microbes in oxygen-poor environments. It can also form in the deep atmospheres of gas giants through high-pressure chemistry. Finding it on Venus, in small amounts high above that scorching surface, opened up a startling possibility. Could something, somewhere in those clouds, be alive? The idea was fragile from the start, and scientists approached it carefully. Other teams re-examined the data, looked with different instruments, and tried to see whether more mundane processes could explain the signal. Some subsequent studies failed to confirm the detection at all. By 2022, several analyses and statements from agencies like NASA leaned toward a cautious conclusion. The initial finding was likely affected by noise and calibration issues. If phosphine was present, it was not yet reliably proven, but the story didn't end there. In 2023, Jane Greaves, the lead author of the original study, reported fresh observations that again hinted at phosphine, this time deeper within the atmosphere. The debate is still ongoing. At the moment, phosphine on Venus sits in a kind of scientific twilight, neither clearly present nor definitively absent, a faint whisper in the data that future missions will need to test more directly. Beyond phosphine, Venus continues to ask quieter questions. How did two planets so similar in size and bulk, Earth and Venus, end up so different in climate and surface conditions? Did Venus ever have oceans of liquid water long ago, before its runaway greenhouse took hold? Exactly how is its atmosphere layered and mixed, and what subtle chemistry is at work in those UV dark patches and high clouds? After a long period of relative neglect, interest in Venus is rising again. Within the next decade, multiple missions are planned or proposed from different parts of the world. Orbiters to map the atmosphere and surface with new precision, probes to dip into the clouds, and even dedicated projects focused on searching for signs of chemistry that might hint at life. Space agencies in the United States, Europe, Russia, China, India, and private groups like those behind the Venus Life Finder concept have all expressed intentions to return. Each mission will look with slightly different eyes, different instruments, different orbits, different questions in mind. Together, they may deepen our understanding of why Venus became what it is, and how worlds like ours can change. Looking at Venus through many kinds of light has already taught us more than visible wavelengths ever could. Radar has drawn out volcanoes and fractures through kilometers of opaque cloud. Infrared has revealed the hot, lower atmosphere glowing beneath that shroud. Ultraviolet has shown puzzling dark streaks hinting at unknown absorbers. All of these pieces help explain why the planet's conditions are so extreme, and why some scientists are still willing to entertain the faint possibility of microbial life in a narrow, temperate layer high above the inferno. For all the allure of distant exoplanets and outer planet moons, you don't actually have to go far from home to find a world worth wondering about. Right here, circling the same star at a gentler distance, is a planet with oceans of liquid water, an atmosphere rich in oxygen, and a strong magnetic field. It has one feature that, as far as we know, is truly unique. It hosts life in all its tangled, fragile forms. It is also the only place we can point to and say, without abstraction, this is home. We live on it every day. And yet there is still so much about Earth that we are only beginning to understand. What makes this small, blue sphere in a quiet corner of the galaxy, so special. How has it changed over time? And what secrets are still written in its shape? People sometimes describe Earth as pear-shaped, or even egg-shaped, as if it were dramatically distorted. That picture is a little misleading. Earth is not a perfect sphere, but its departures from roundness are gentler and more subtle than those words suggest. Small hints in its curves that tell a long story of spin, gravity, and shifting rock beneath our feet. If you could hold Earth in your hands and turn it slowly, you'd notice it's not quite a perfect sphere. It's a little wider at the middle than from top to bottom, bulged very slightly at the equator, squeezed gently at the poles. That extra width is only about 45 kilometers, a tiny difference compared to the planet's full size of about 12,742 kilometers across. The bulge comes from Earth's spin. As it rotates, material near the equator feels a small, outward tug, and over long stretches of time, the whole planet settles into that almost round, gently swollen shape. Because of this, the point on Earth that sits farthest from the planet's center isn't the summit of Mount Everest. It's actually the top of Chimborazo, a volcano in Ecuador, which lies close to the equator and gets an extra lift from that equatorial bulge. In a way, Chimborazo is a quiet reminder that even something as simple as highest depends on how you measure. People have been trying to understand Earth's shape and place in the universe for a very long time. Long before rockets and telescopes, ancient thinkers looked at shadows, stars, and ships disappearing over the horizon and tried to piece together where we live. By the 6th century BCE, some Greek philosophers were already speaking of a round Earth. But it wasn't until around 240 BCE that someone tried to measure its size with numbers. That someone was Eratosthenes. He heard that in Syene, a city in southern Egypt, the sun stood directly overhead at noon on the summer solstice, no shadow in a deep well. In Alexandria, farther north, the sun still cast a shadow at the same time. By carefully measuring the angle of that shadow and knowing the distance between the two cities, he could work out what fraction of a full circle that angle represented. From there, he estimated Earth's circumference. His result was surprisingly close, within about 5 to 10% of modern values, all from sunlight, geometry, and patient thought. Centuries later, another shift arrived. In the 16th and early 17th centuries, the idea that Earth sat still at the center of everything gave way to a new picture. Nicolaus Copernicus proposed that the Sun, not Earth, was at the center of the solar system. Johannes Kepler refined the orbits with careful mathematics, and Galileo Galilei brought telescopic evidence. Moons circling Jupiter, phases of Venus, things that only made sense if Earth was not the hub of the cosmos. Bit by bit, we came to see our planet as one world among many, moving rather than being moved around. Now we know that Earth is the third planet from the Sun, one of 4 inner rocky worlds. It orbits at an average distance of about 150 million kilometers, sometimes closer around 147 million kilometers at perihelion, and sometimes farther, about 152 million kilometers at aphelion. One full orbit takes what we call a year. That sounds simple. 1 year, 1 trip. But underneath that simplicity, the rhythms are a little messier. Earth doesn't take exactly 365 days to go around the Sunday. The real figure is about 365¼ days. That extra quarter of a day accumulates. If we ignored it, our calendar would drift, and seasons would slowly slide out of sync with the months. Every 4 years, we catch up by adding a leap day, folding those 4 quarters into an extra date. Months carry their own quiet story. The word month is tied to moon, a hint that these slices of time once tried to track the moon's cycle. The moon takes about 27.3 days to orbit Earth, which does not divide cleanly into our 365.25-day year. It would be awkward to fit only lunar months into a solar year without constantly adjusting. So most calendars have settled into a compromise that no longer follows the moon exactly. The link remains in language, even if not in precise timing. Even the day, the unit we feel most directly, is not as simple as 24 hours of a spinning planet. If you measure how long it takes Earth to rotate once relative to distant, fixed stars, a sidereal day, it's about 23 hours and 56 minutes. Our clocks, though, mark 24 hours. Those extra 4 minutes each day are tied to our orbit. As Earth moves along its path around the Sun, it has to turn a little more than 360 degrees for the Sun to appear in the same spot in the sky as the day before. It's that extra twist that stretches the sidereal day into a solar day. Because Earth's orbit is slightly elliptical and its axis is tilted, the length of a true solar day wobbles by up to about 30 seconds over the course of a year. To keep life navigable, we smooth over those variations and define a mean solar day, an average that becomes our steady 24 hours. Meanwhile, tides raised by the moon are quietly tugging on Earth's rotation, stealing a tiny bit of spin energy and turning it into heat. Over long stretches of time, that drag lengthens our days. Right now, it's on the order of about 0.02 of a second per century. 500 million years ago, models suggest a day on Earth might have been less than 22 hours, and there may have been around 400 days in a year. You can see Earth's rotation written in the sky with a long exposure photograph. Point a camera toward the stars at night and leave the shutter open. The stars will trace arcs across the image as the planet turns beneath them. Near the poles, those arcs curl into circles around a central point, the projection of Earth's axis into the sky. From the ground, it feels like the heavens are moving. In reality, we are spinning gently inside them. Combine that spin with Earth's orbit, and you get another delicate pattern, the analemma. If you took a picture of the Sun from the same spot and at the same clock time every day for a year, then layered those pictures together, the Sun's position would trace a figure-8 shape in the sky. The up and down part of that pattern comes from Earth's axial tilt, 23.5 degrees, relative to the plane of its orbit, changing how high the Sun climbs through the seasons. The sideways wobble comes from the elliptical shape of our orbit, and from the same timing differences between true solar days and the mean solar day. Each planet would draw its own unique analemma, shaped by its tilt, its orbit, and its rotation. Ours is a slender, tilted 8, a quiet signature of how Earth leans and circles and spins. That tilt is also what gives us seasons. In summer, for a given hemisphere, that half of Earth leans toward the Sun. In winter, it leans away. It's natural to imagine that being physically closer to the Sun in summer is what brings warmth, but on the scale of 150 million kilometers, the small differences in distance during an orbit are not the main driver. At perihelion, Earth is about 5 million kilometers closer to the Sun than at aphelion, yet perihelion occurs in early January midwinter in the northern hemisphere. The key is angle, not distance. When the Sun is high in the sky, its light falls more directly, and its energy is concentrated on a smaller area of ground. When it is low, the same amount of sunlight spreads out over a broader patch, thinning its effect. In summer, days are also longer, giving the surface more hours to absorb warmth. In winter, shorter days and lower sun angles mean less energy. That difference in heating shapes winds, currents, and weather, breathing life into the pattern of seasons. Above all of this, hugging the planet, is our atmosphere. Compared to the thick cloaks of Venus or Titan, Earth's atmosphere is modest in mass, but it's dense enough at the surface to matter enormously for life. It's made mostly of nitrogen, about 78%, along with around 21% oxygen and roughly 1% argon, plus tiny amounts of other gases like carbon dioxide. Water vapor floats among these in varying amounts, from almost nothing in cold, dry air to a few percent in warm, humid conditions. Averaged together, water vapor makes up about 1% of the whole. Ozone, a form of oxygen with 3 atoms per molecule, gathers in a layer high above the surface. That ozone layer absorbs much of the sun's harmful ultraviolet radiation, shielding living things on land from damage. The atmosphere does many jobs quietly. It supplies oxygen for animals and plants that need it, and carbon dioxide for those that use it to build sugars and release oxygen in return. It catches and burns up countless small meteoroids that would otherwise strike the ground. It spreads heat around the globe and softens temperature extremes. Without any air to trap outgoing infrared radiation, Earth's average surface temperature would be around 8 degrees Celsius instead of the current plus 15 degrees Celsius. The atmosphere makes our world less harsh, more habitable, a little more forgiving. Within that air, the water cycle moves constantly. Sunlight warms oceans, lakes, and soils, lifting water molecules into the atmosphere as vapor. As the vapor rises, it cools and condenses onto tiny particles of dust or salt, forming clouds, collections of droplets, or ice crystals light enough to float. Winds carry those clouds far from where they formed. Eventually, the water falls back as rain, snow, or sleet, returning to rivers, ground, and seas. Along the way, it erodes rock, carves valleys, nourishes plants, and threads through the bodies of living things. Every sip you take has been around this loop many times over, through roots and clouds and stones. Most of Earth's liquid water rests in the oceans. They cover about 70% of the planet's surface and make up roughly 1/1400th of Earth's total mass. If you could somehow smooth out every mountain and trench, filling every valley, the water would spread into a global ocean about 3 kilometers deep. Instead, we have continents and basins, peaks, and deep seafloor trenches, a relief map sculpted by forces from below as much as by water and wind from above. Under the crust, Earth's mantle is hot and slowly flowing on geological timescales. The solid surface we stand on is broken into rigid plates that move atop that underlying material. Where plates meet, they push, pull, and slide past one another. Their interactions raise mountain ranges, open ocean basins, create deep trenches, and feed lines of volcanoes. Earthquakes mark their shifting boundaries. From a human perspective, these events can be dangerous, sudden, and frightening reminders that the ground is not as fixed as it seems. But over millions of years, plate tectonics refreshes the planet. Old crust is recycled into the mantle. New crust is created at ridges. Nutrients are lifted from deep rocks and spread across the surface. This continual renewal keeps Earth's face varied and its environments dynamic, providing the changing stage on which oceans, climates, and life itself can evolve. Seen this way, our world is a balance of motions and cycles, spins and orbits, seasons and tides. air and water, solid rock, shifting slowly beneath an atmosphere that both protects and transforms. We notice only small parts of it in daily life: the length of the day, the turn of the seasons, the feel of a breeze. But beneath those familiar sensations, the planet is quietly, patiently weaving its own long story. Deep under everything familiar, beneath soil, stone, oceans, and drifting plates, Earth has a heart of metal. Below the moving mantle lies the core, made mostly of iron and nickel. It's this heavy center that makes Earth the densest planet in the solar system, with an average density of about 5.5 grams per cubic centimeter. A lot of that weight is hidden from you under thousands of kilometers of rock. The outer core alone stretches to roughly 5,000 kilometers across, a vast shell of liquid metal swirling slowly around the planet's center. Inside that, the inner core is thought to be solid, an iron-nickel sphere, held in place by pressures so high they're almost hard to imagine, around 360 gigapascals, hundreds of billions of times the air pressure at sea level. Temperatures there climb to about 6,000 degrees Celsius, similar to the surface of the sun. Yet, the iron does not melt, because the pressure squeezes it into solidity. This restless metallic heart does more than just sit there. As the liquid outer core moves and churns, it turns motion into electricity. The flow of conducting metal in the presence of rotation and heat creates a self-sustaining dynamo, a planetary generator that wraps Earth in a magnetic field. You can picture it, roughly, as the field of a giant bar magnet tilted inside the planet, with lines of invisible force arcing from one hemisphere to the other. That field quietly guards the surface. The sun is constantly sending out a wind of charged particles, electrons and ions flying through space at high speed. When that wind reaches Earth, most of it is diverted around the planet by the magnetic field, guided into curved paths that slide past us instead of straight through. Without this shield, solar storms would regularly blast the upper atmosphere, stripping it away over time and showering the surface with radiation strong enough to damage DNA on a planetary scale. Because of the field, most of those particles never touch the air directly. A small fraction, though, spiral down along the magnetic field lines near the poles. There, they collide with atoms and molecules. In the upper atmosphere, oxygen, nitrogen, and those particles glow briefly before slipping back to their normal state. To someone standing under a dark sky in the far north or south, that glow appears as the aurora, soft curtains and arcs of light shifting silently across the stars. On Earth, the most common color is green, mostly from excited oxygen high above the ground. It's a beautiful side effect of a process that could have been purely destructive. Earth has another companion that shapes its story: the moon. Other planets have moons, some with dozens, but Earth's is unusually large compared to its host. Because of its size and closeness, we see it not as a tiny speck, but as a full, textured world in our sky. Craters, seas, subtle shades. You can pick out details with the naked eye on a clear night. That presence is more than just decoration. The moon's gravity tugs on Earth's oceans, pulling the water into two bulges, one facing the moon, one on the opposite side. As Earth rotates beneath these bulges, coastlines pass through them, and we feel that passing as tides, the slow rise and fall of sea level over the course of a day. The solid Earth moves, too, just a little. Rock is not as free to flow as water, but it still flexes under the pull. The entire crust rises and falls by tiny amounts, invisible in daily life but real. those repeated stretches and squeezes add up over time. Some researchers think that this steady kneading may help keep Earth's interior lively, contributing in a small way to the heat and motion that drive plate tectonics. The same tides that move shorelines and shape coastal life might also, very gently, be stirring the deep engine that renews the surface. When you step back and think of all these layers, core, field, atmosphere, water, moon, it's easy to feel a quiet amazement at how many conditions had to line up for a world like this to exist. Enough mass for a molten core and a magnetic shield, enough distance from the sun for liquid water, a tilt for seasons, but not so extreme that the climate tears itself apart, a large moon to steady the planet's spin and stir its interior. Out of those conditions, life emerged and eventually began wondering about its own origins, building instruments, launching probes, and looking back at Earth from above. From orbit, our planet appears almost fragile, a blue and white sphere with thin swirls of cloud, a faint haze of atmosphere, and dark land masses threaded with rivers and lights. It looks complete in a way that is hard to put into words, both vast and intimate at once. And yet, for all its uniqueness, Earth is not alone. Nearby, other worlds circle the same sun, each with its own history and flavor of beauty. One of them, a little farther out, has been a favorite in our collective imagination for a long time: Mars. In telescopes and photographs, Mars wears a reddish hue, its dust and rocks rich in iron oxides that reflect sunlight in warm tones. For centuries, people have looked at that color and wondered if something stirred there. Canals, civilizations, hardy plants clinging to a colder Sunday. Science has brushed away the old stories and replaced them with more careful, quieter ones. But the fascination remains. It's one of our closest neighbors, and in some ways it feels almost familiar. If you could stand on Mars, you might be surprised at how normal the rhythm of the day feels. A Martian solar day, called a sol, is only slightly longer than an Earth day, about 24 hours, 39 minutes, and 35 seconds. You would still see a sunrise and sunset every day. Still feel the slow, repeating arc of time that you're used to, just stretched by less than an hour. Mars's year is longer, roughly 1.88 Earth years, or about 687 Earth days. That makes sense for a world with a larger orbit, farther from the Sunday. But its axial tilt is close to ours, about 25 degrees, compared to Earth's 23.5. Because of this, Mars has seasons that feel conceptually similar to ours. It leans toward the sun and away, trading summer and winter between hemispheres, in a way that would be easy to recognize on a sketch, even if the details on the ground differ. Those details do differ. Temperatures on Mars swing more dramatically than most of us experience on Earth. In winter at the poles, under continuous darkness, they can drop to around 143 degrees Celsius. In summer near the equator, under a high sun, they can climb to about 35 degrees Celsius on a warm afternoon. The air there is thin, so the warmth is fragile. But the idea of a frosty dawn giving way to a relatively mild midday is not entirely alien. Mars has polar caps, two bright white patches at the top and bottom of the planet. Like ours, they contain water ice, but that's not the whole story. In winter, when a pole tilts away from the sun, the air above it becomes so cold that part of the carbon dioxide atmosphere itself freezes out, settling as dry ice slabs on top of the permanent ice cap. In spring, as sunlight returns, that frozen carbon dioxide sublimates directly back into gas. The caps grow and shrink with the seasons, breathing in and out with each Martian year. Seen from above, the polar caps are etched with beautiful spiral troughs, curving channels winding around the pole like the grooves on a seashell. These are thought to arise from a mix of winds, snowfall, and the Coriolis effect on a rotating planet, slowly carving patterns in layered ice over many cycles. As the dry ice sublimates, it doesn't just disappear quietly. The gas can rush out through vents and fractures, helping to stir the atmosphere and drive winds. At times, those winds can reach speeds of up to 400 kilometers per hour, powerful enough, even in thin air, to lift fine dust and help shape the planet's weather. For all these echoes of home days, seasons, polar caps, Mars is still smaller and lighter than Earth. Its diameter is about 6,779 kilometers, just over half of Earth's. Its lower mass and slightly different composition make its gravity weaker. At the surface, the pull you feel is about 38% of what you feel here. If you weigh 100 kilograms on Earth, you would weigh only about 38 kilograms on Mars. You would walk with a lighter step, objects would fall more slowly, and jumps would carry you farther. Interestingly, that surface gravity is only a little stronger than on Mercury, even though Mars is substantially larger in size. This comparison hints at how dense Mercury is relative to Mars, how much iron and heavy material it packs into a smaller volume. Weaker gravity on Mars allows for structures that would be hard to sustain on Earth. The most famous example is Olympus Mons, a vast shield volcano rising from the western side of the planet. It stands about 22 kilometers above the surrounding plains, roughly 3 times the height of Mount Everest above sea level. But unlike Everest, which is jagged and sharply peaked, Olympus Mons is broad and gentle. Its base stretches more than 600 kilometers across, and its slopes average only about 5 degrees. If you stood on its summit, you might not feel as though you were on a mountain at all. The curve of the planet and the low slope would hide much of the volcano beneath the horizon. Along its edges, Olympus Mons ends in steep cliffs up to 8 kilometers high, dropping from the smooth flanks down to the plains below. The top contains a complex of collapsed craters, calderas, where the ground once swollen with magma has sagged back down as the internal supply retreated. From orbit, the volcano looks almost like a giant blister, frozen mid-swell. If Olympus Mons is Mars's great summit, then Valles Marineris is its great scar. Stretching along the equator, this canyon system runs for more than 4,000 kilometers, about a quarter of the planet's circumference. In places, it reaches depths 4 times greater than the Grand Canyon and widths of up to 200 kilometers. Standing with your mind on one rim, you could imagine a landscape falling away into shadow, cliffs layered with rock and dust, and a sky that spans a gulf no human has yet seen in person. Its scale is almost beyond direct experience, but in the quiet of night, when the world around you is still, it can be strangely soothing to think that somewhere out there, under the same stars, a red planet carries a canyon deep enough to swallow mountains. When you picture Mars, the first thing that usually comes to mind is its color. Even from far away, it wears that soft, rust-red glow. Up close, that color becomes more personal. Dusty soil, faded rocks, pale pink skies near the horizon. The reason is simple and slow. Mars's surface is rich in iron-bearing minerals. Over long ages, those minerals have reacted with a little bit of oxygen available to form iron oxide rust. The planet has, in a sense, quietly rusted, grain by grain, until its face took on that reddish-brown hue. Rovers have sent back countless images of this rusted world. In their high-resolution views, you can see the fine texture of sand, the layered edges of eroded rock, the scattered pebbles that look close enough to nudge with your boot. It's strange and a little moving to realize that these are not computer paintings or imagined scenes. They're genuine photographs from another world, the kind of clarity early astronomers could only dream about. From Viking to spirit, opportunity, curiosity, and perseverance, each mission has added new pages to Mars's album of arid vistas. At first glance, these views can give the impression of a frozen, silent planet, everything dry, everything finished. But Mars is not as still as it seems. Even without lakes and forests, it is still changing, still active in its own quiet way. Orbiters watching from above have caught sudden events in the act. In 2008, one of them happened to be looking at a steep, icy cliff just as an avalanche occurred. In a series of images, you can see bright material and dust cascading down, hitting lower slopes and flinging up a cloud. The dunes nearby, some up to hundreds of meters tall, frame the scene, and the dust plume spreads like breath in cold air. Even in such thin atmosphere, gravity still pulls, slopes still fail, and cliffs still crumble. Elsewhere, strange patterns appear on the ground every spring that look, at first sight, like dark spiders radiating out from a central point. They're not living creatures, of course, but the shapes are eerie. During the long winter, carbon dioxide from the atmosphere settles as dry ice over the polar regions, forming a clear slab. As spring sunlight returns, it warms the ground underneath that slab first. The ice touching the ground begins to sublimate, turning directly from solid into gas, while a still frozen roof of ice remains above. Pressure builds in the trapped gas until it finds a weak spot and bursts upward, carrying darker dust and sand from below with it. That material falls back onto the surface in branching streaks around the vent. Seen from orbit, those dark, radiating marks look like spiders etched into the ice. Some can reach hundreds of meters across. They're reminders that even without liquid water, Mars has its own cycles of freeze and thaw, build up and release. Rovers and orbiters have also watched dunes change shape over the course of months. A ridge that looked smooth one season might appear sharper and more sculpted the next, its face subtly rearranged by the wind. Camera teams have returned to the same dune fields again and again, building time-lapse records that prove the sand is migrating grain by grain. Fresh impact craters tell their own stories. A new crater often throws bright material outward, dust and ice uncovered from beneath the usual reddish surface. Some images show streaks of white and blue tinted deposits in false color indicators of water ice that was hidden just below the ground. In at least one case, after an impact exposed such ice, melt and flow patterns appear to trace away downhill, marking where the ice briefly softened or sublimated, disturbing the soil as it went. For all of this subtle motion, Mars is also home to some of the most dramatic weather in the solar system. When strong winds sweep across its dusty plains, they can lift fine particles into the air and build storms of astonishing scale. Some remain local swirling clouds that cover a region for a few days. Others grow, join, and swell, spreading until they wrap much of the planet in a hazy, copper-colored shroud. From orbit, you can watch a storm bloom over a week. The surface features soften and fade, the edges of the polar cap blur, and the whole globe takes on a smoother, more muted look. Then, as the winds calm, the dust slowly settles back out, revealing the familiar shapes of craters, valleys, and volcanoes again. Near the poles, storms can push dust out over the cap, leaving faint tan stains across the white. Global dust storms like this have been seen more than once. They're large enough to be visible from Earth through telescopes, and intense enough to darken the skies over rovers for days, sometimes weeks. Within these storms, and even on calm days, smaller whirlwinds dance across the ground. These are dust devils, thin columns of rising, spinning air that pick up loose particles and trace looping paths over the surface. From orbit, they appear as slender plumes with long shadows, sometimes hundreds of meters high and tens of meters wide. On the ground, rovers have watched them glide past, the sky dimming slightly as they cross between the sun and the camera. The nearby sand momentarily stirred. Their tracks, left behind as cleaned or darkened streaks, weave across dunes and plains like faint handwriting. With all these events, avalanches, geysers, storms, whirlwinds, you might imagine Mars has an atmosphere similar to Earth's, but it doesn't. The air there is extremely thin. To find a similar pressure on Earth, you would have to climb to an altitude of around 36 kilometers or more, far above the cruising height of airliners, high into the stratosphere. It's a place where an unprotected human would quickly lose consciousness. Almost all of Mars's atmosphere is carbon dioxide, about 96% with a little nitrogen and argon. There's virtually no oxygen to breathe. Any visitor would need not just an oxygen supply, but a pressure suit, something to hold enough air around their body to stay comfortable. The low pressure is one reason liquid water can't persist on the surface today. It tends to freeze or boil away instead. Yet even such a thin atmosphere can give rise to beauty. Some of the most delicate images from Mars show sunsets and sunrises. Near the horizon, the sky takes on a bluish tint around the sun, while the rest of the sky remains more of a butterscotch color. The fine dust in the air scatters sunlight differently than air on Earth does. Red light is scattered more strongly, leaving a cooler glow in the sun's direction at the moment it dips below or rises above the edge of the world. In those moments, the planet feels almost gentle. Evidence carved into the landscape tells us that Mars's air was not always so tenuous. Dry riverbeds, deltas, and ancient lake basins show that water once flowed under open skies. For that to happen, the atmosphere must have been thicker and warmer, able to hold in enough heat and pressure for liquid water to exist. Over billions of years, something changed. A leading idea is that Mars lost much of its magnetic field early in its history. Without a strong field to deflect the solar wind, the upper atmosphere became vulnerable. Energetic particles from the sun could strip away lighter gases, atom by atom, in a process that continues even now. Spacecraft have detected charged particles streaming away from Mars, peeled off the edge of the atmosphere, and carried downstream along the planet's orbital wake. Slowly, the blanket thinned, the greenhouse effect weakened, and surface water retreated into ice and rock. Mars still keeps companions of its own in the sky. Two small moons, Phobos and Deimos, orbit it in quiet loops. They're not round like Earth's moon, but irregular, more like captured asteroids, potato-shaped, cratered, and dark. From the surface, they do not dominate the sky in the same way our moon does. Phobos, the larger and closer of the two, rises and sets quickly, crossing the sky in just a few hours. Because it orbits only about 6,000 kilometers above Mars's surface, it appears noticeably larger than Deimos, but still smaller than Earth's moon looks to us. Deimos, farther out and smaller, would be just a bright point, a tiny moonlet drifting along a slow, predictable path. Despite their modest size, they offer moments of quiet drama. Rovers have filmed Phobos passing in front of the Sun, creating a kind of partial eclipse. In these sequences, you can watch its lumpy silhouette slide across the bright disk, the light dimming slightly, and the ground around the rover falling into a softer shade for a few moments. It's a strangely intimate reminder that eclipses are not unique to Earth. Wherever there are moons and stars and planets, shadows will cross and align. And from Mars, if you look back toward home with a sensitive enough camera, Earth is just a point of light. In some images, you can make out a faint star-like dot with a smaller dot beside it. That's Earth with its moon, as seen from tens of millions of kilometers away. There's no hint in those pixels of oceans or forests, cities or storms, only a tiny, pale bead hanging in a dark sky. It's humbling to think that every person you've ever known, every story that has unfolded here, all take place on that small point. Just as Mars appears to us as a wandering red spark among the stars, we appear to Mars as one more tiny light. In the quiet of the night, when your own sky is clear, it can be comforting to remember that. Worlds observing worlds, each carrying its own weather, its own history, its own slow, unfolding changes under the same wide universe.